In mathematics, the real number may be described in different ways. In short, real numbers include both rational and irrational numbers. Real numbers are used in measurement of continuously varying quantities such as size and time. In this chapter, we will study the following concepts. First, Introduction to Numbers. Second, Euclid's division lemma and algorithm. Third, the fundamental theorem of arithmetics. Fourth, irrational number. Fifth, decimal expansion. Introduction to Numbers. Natural numbers. Natural numbers are the set of numbers used to count objects starting with the number 1, then 2, 3, 4, and so on. Whole numbers. The set of whole numbers includes the set of natural numbers with the addition of 0. Integers. The set of integers includes the set of whole numbers with the addition of negative whole numbers. Rational numbers. Rational numbers include any number that can be written as a fraction with an integer for the numerator and a non-zero integer for the denominator. Rational number also includes all terminating decimals and all repeating decimals. So we can conclude that all natural numbers are included in whole numbers and all whole numbers are included in integers and all integers are included in rational numbers. The irrational numbers include numbers such as the square roots of numbers that are not perfect squares, or we can say that those numbers which are non-terminating and non-repeating. Real numbers. Irrational numbers and rational numbers together form the set of real numbers, which include every number that makes up the number line. Let us understand prime and composite numbers. Prime numbers are those numbers that have exactly two factors, 1 and the number itself. For example, factors of 2 are 1 and 2 itself. Factors of 3 are 1 and 3 itself. Factors of 5 are 1 and 5 itself. So they have exactly two factors and are called prime numbers. Composite numbers are those numbers which have more than two factors. For example, factors of 4 are 1, 2, and 4. Factors of 6 are 1, 2, 3, and 6. Factors of 8 are 1, 2, 4, and 8. So they have more than two factors and are called composite numbers. Did you know the numbers of primes are infinite? There is no large prime number. Every prime number other than 2 is an odd number. All other even numbers are composite numbers. Let us know prime and composite numbers from 1 to 100. Number 1 is the only number which is neither a prime number nor a composite number. Number 2 is the smallest prime number. The encircled numbers are prime numbers. The crossed out numbers are composite numbers. Hence, there are 25 prime numbers and 74 composite numbers from 1 to 100. Let us understand the concept of Euclid's division lemma, which states that for given two positive integers a and b, there exists unique integers q and r such that a equals to bq plus r, where r is greater than or equal to 0 but less than b. For example, let a equals to 23, b equals to 5. Then 23 equals to 5 into 4 plus 3, where 3 is greater than equal to 0, less than 5. Euclid's division algorithm is based on this lemma. Let us understand Euclid's division algorithm. It is a technique to obtain HCF and GCD of two given positive integers, say a and b, where a is greater than b by successive use of Euclid's division lemma. Now we understand the steps to be followed in this algorithm with example. Step 1. Apply Euclid's division lemma to a and b, so we find two whole numbers q and r such that a equals to bq plus r, where r is greater than equal to 0, less than b, like in example, if a equals to 225, B equals to 135, then 225 equal to 135 into 1 plus 90, where 90 is greater than equal to 0 and less than 135. Step 2. If R is equal to 0, then HCF of A and B are equal to B. But if R is not equal to 0, then we again apply Euclid's lemma to B and R, like in example, R is equal to 90, which is not equal to 0, so we again apply Euclid's division lemma to B and R. By taking A is equal to 135, B is equal to 90, and get 135 is equal to 90 into 1 plus 45, where 45 is greater than equal to 0 but less than 90. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Like in example, R is equal to 45, which is not equal to 0, so we again apply Euclid's division lemma to B and R by taking A is equal to 90 and B is equal to 45, and get 90 is equal to 45 into 2 plus 0, where R is equal to 0. Therefore, HCF of 225 and 135 is equal to 40. Let us understand the concept of fundamental theorem of arithmetics. According to this theorem, every composite number can be expressed as product of primes, and this factorization is unique apart from the order in which the prime factors occur. This theorem states two facts about composite numbers. First is every composite number can be factorized as product of primes. For example, factorization of 154 is 7 into 2 into 11, where all are prime numbers. This factorization is unique apart from the order in which the prime factors occur, as 7 into 2 into 11 can be written as 2 into 7 into 11 or 11 into 2 into 7. Example, let us express 1771 as a product of prime factors. Solution. On dividing 1771 by 7, we get 253. On dividing 253 by 11, we get 23. On dividing 23 by 23, we get 1. Therefore, prime factors of 1771 are 7, 11, and 23. Application of prime factorization. We can find HCF and LCM of given numbers by using the prime factorization method. How to find? First, find prime factors of all given numbers. For example, let two numbers be 26 and 91. When the prime factorization of 26 is equal to 2 into 13, the prime factorization of 91 is equal to 7 into 13. The HCF is equal to the product of the least powers of each common prime factors. Therefore, the HCF of 26 and 91 is equal to 13, and the LCM is equal to product of the greatest powers of each prime factors. Therefore, LCM of 26 and 91 is equal to 2 into 7 into 13 is equal to 182. Important result. Let A and B be any two positive integers, then HCF of A, B into LCM of A, B is equal to A into B. Here is an example to understand this fact. Example. Given that HCF of 306 and 657 is equal to 9, find the LCM of 306 and 657. Solution. A is equal to 306, B is equal to 657, and HCF of 306 and 657 is equal to 9. We know that HCF of A, B into LCM of A, B is equal to A into B. Therefore, LCM of A, B is equal to A into B divided by HCF of A, B. The LCM of 306 and 657 is equal to 306 into 657 divided by HCF of 306 and 657 is equal to 306 into 657 by 9 is equal to 2,01,042 by 9 is equal to 22,338. Irrational number. Example. Prove that root 3 is an irrational number. Solution. Let, if possible, root 3 be a rational number. Then we can find two coprimes P and Q where Q is not equal to 0 such that root 3 is equal to P by Q. This implies root 3Q is equal to P. On squaring both sides we get 3Q square is equal to P square, equation 1. This implies 3 divides P square. This implies 3 divides P, equation 2. Because if P divides B square, then P divides B, where B is a positive integer. This implies P is equal to 3K for some integer K. This implies P square is equal to 9K square, equation 3. By 1 and 3, we get 3Q square is equal to 9K square. This implies 3 divides Q square. This implies 3 divides Q, equation 4. Because if P divides B square, then P divides B, where B is a positive integer. 2 and 4 implies that 3 is a common factor of P and Q. But this contradicts the fact that P and Q are coprimes. So our assumption that root 3 is rational is incorrect. Hence, root 3 is an irrational number. The sum or difference of a rational and irrational number is irrational. Let us learn this concept through this example. Show that 5 minus 2 root 3 is an irrational number. Solution. Let, if possible, 5 minus 2 root 3 be a rational number. So we can find P and Q where Q is not equal to 0 such that 5 minus 2 root 3 is equal to P by Q. This implies 5 minus P by Q is equal to 2 root 3. This implies 5Q minus P divided by 2Q is equal to root 3. LHS is rational since P and Q are integers. This implies root 3 is a rational number. But this contradicts the fact that root 3 is irrational. Therefore, our assumption is wrong, and so 5 minus 2 root 3 cannot be rational. This implies 5 minus 2 root 3 is an irrational number. Theorem 1. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form P by Q, where P and Q are coprime, and the prime factorization of Q is of the form 2 raised to the power n, 5 raised to the power m, where n and m are non-negative integers. Here is an example to understand this theorem. Let x equal to 0.25 be a rational number whose decimal expansion terminates. Then x equals to 0.25 can be written as 25 by 100 or x equals to 1 by 4, where 1 and 4 are coprimes. Now 1 by 4 equals to 1 by 2 raised to the power 2 into 5 raised to the power 0. So prime factorization of denominator 4 is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Converse of theorem 1. Let x is equal to P by Q be a rational number such that the prime factorization of Q is of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. Then x has decimal expansion which terminates. Here is an example to understand this theorem. Let x is equal to 19 by 20 be a rational number Here q is equal to 20 and prime factorization of 20 is equal to 2 into 2 into 5, or is equal to 2 raised to the power 2 into 5 raised to the power 0, which is of the form 2 raised to the power n into 5 raised to the power m. So, 19 by 20 is equal to 19 divided by 2 raised to the power 2 into 5, or is equal to 19 into 5 divided by 2 raised to the power 2 into 5 into 5, or is equal to 95 by 100, or is equal to 0.95, which has terminating decimal expansion. Theorem 2. Let x equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating but repeating. Here is an example to understand this theorem. Let 129 by 210 be a rational number where 129 and 210 are coprimes. Here q is equal to 210 and prime factorization of q is equal to 2 into 3 into 5 into 7, which is not of the form 2 raised to the power n into 5 raised to the power m. So 129 by 210 has a non-terminating and repeating decimal expansion.